Sometimes we have multiple vectors, and what we really need to do is be able to add them together. This video is about how to do that. We've already been actually adding vectors for a while, secretly. They've been one-dimensional vectors, but it still counts. If I tell you I'm walking 3 miles east, then 1 mile east from there, you would say without hesitation that I'm walking a total of 4 miles east, right? If I start here, say I go 3 miles east, and then from there I'm going to go 1 mile east, you could pretty quickly tell me, well, you have gone a total of 4 miles east. And what I'm doing, I'm saying vector A is 3 miles in the x direction. Vector B is 1 mile in the x direction. So vector C is 4 miles in the x direction, which I got by adding vector A and vector B. Now, I didn't do all those things with instructions and with labels and everything in my head. I just said, well, it's 3 and it's 1 more, that's 4. If I walk 3 miles east and then I turn and walk 1 mile west, you would tell me I am 2 miles from where I ended, or from where I started. And again, I'm doing the same thing. Vector A is 3 miles in the x direction. Vector B is negative 1 mile in the x direction because I'm pointing to the left. So vector C is 2 miles in the x direction, and I got that by taking vector A and adding it to vector B. We have an intuitive understanding of adding vectors, at least in one dimension. If I started by walking 3 miles east, because that seems to be the thing to do, and then I went 4 miles north, I would actually know what to do with that already. This is reconstructing a vector from components, which is what we just did. We would say this is the same as doing this sort of thing. Here's vector A, which is 3 miles in the x direction. Here's vector B, which is 4 miles in the y direction. And here's vector C, which is vector A plus vector B, the result of walking along path A plus the result of walking along path B afterwards. That's what C is. I know from a previous video that this is going to come out to be 5 miles, and that this angle is going to come out to be 53 degrees, and I am looking north of east. So I can do that. I know how to do that when these vectors are already components. What if my vectors are not so nice? What if I start out walking 3 miles east, and then after that I walk 10 miles at 53 degrees north of west? So 10 miles, 53 degrees north of west, something like that. How do I add those together? What I'm looking for in the end is a path that connects my beginning point to my end point. So let's do some labeling. Here is vector A, and that is 3 miles in the x direction. I am saying, let's let my x direction be horizontal and my y direction be vertical. So vector A points in the x direction. Vector B, well, that's got some stuff going on. And vector C, I don't even know what to do with that yet. I'm going to take vector B and break it into components. What I've got right now is a vector that looks like this, and I know this is 10 miles. I'm going to break that into an x component. This thing points to the left and up, so to the left is the x component, and up is the y component. This is going to be bx, by, and this is just b. Without a vector sign, that is saying this is the magnitude of vector b. I also know that this angle in here is 53 degrees. So I'm going to use my trig functions to find what bx and by are. Bx is the side that's adjacent to my angle, so this is going to be equal to b times cosine is the one that goes with adjacent, 53 degrees. By is the opposite side, that's the one that's going to go with the sine of 53 degrees. Okay, the cosine of 53 degrees is 0.6. 0.6 times 10 miles, that is 6 miles. The sine of 53 degrees is 0.8. 0.8 times 10 miles, that's 8 miles. So I have my bx, I have my by. What I would like to do now is take these and make a table. And I know, not everyone wants to make a table, not everyone wants to do all of the extra steps that just feel like bookkeeping. But what I have found in my experience is that for the types of students who take this course, once you have your information organized, once you have a definitive starting point, you can do most anything. Setting up this table is a way to organize thoughts, and it's kind of your immediate starting point. You don't end up staring at a blank page for any amount of time. You have a, what do I do? How do I start this problem? Well, I know I can make a table. Let me start there. It's having a first step, and that helps a lot. So vector A, vector B, vector C. I'm going to look at x components and y components. I'll move the screen over in just a moment. Guess the moment has come. In the end, I'm going to get vector C by adding vectors A and B. So let's see what we've got. Vector A points to the right. It's 3 miles. It has an x component of 3 miles and a y component of 0. Vector B points to the left by 6 miles, so negative for the x component, and points up 8 miles. And then because vector C, let me write it this way, because vector C is just these two added together, I can add the components. This is what I've done before. Horizontally, what I'm saying, I've moved 3 miles east and then 6 miles west. So we know I'm going to end up being 3 miles west of where I started, and that's what I get. 3 minus 6, that's negative 3. Vertically, 0 plus 8, that's 8. And now I have vector C. Now I can give an answer that looks like that. I can say vector C is negative 3 miles in the x component plus 8 miles in the y direction. That's fine. It gives information about magnitude and about direction. It's a set of directions that gets me from my starting point to where I need to go. If I move 3 miles to the west and 8 miles north, that is my end point. So this is a valid form for giving an answer. This is called the component form of a vector. But sometimes the question that we're asked is, how far are you from where you started? Or what direction do you have to travel to get to where you're going? In that case, I actually do need a magnitude. So vector C, I'm going to reconstruct. I have that I point 3 miles to the west, so Cx is 3 miles. I'm not going to put in the negative because I'm taking care of that by having it point to the left. And then cy is 8 miles. Here is my total vector. I'm going to get c using Pythagorean theorem. So I get a square root of 3 miles squared plus 8 miles squared. 8 squared is 64, 3 squared is 9, the square root of 73, 8.54. I have what my diagonal is, but then I'm also going to need a direction, an angle. So let me do that. There is my angle, and I know that the tangent of my angle is going to be cy over cx. So my angle will be the inverse tangent of 8 miles over 3 miles, which works out to be something like 69.4 degrees. That angle, I am facing west and turning toward the north, so this is north of west. I can give my answer that way as well. I can say my vector c is going to be 8.54 miles at 69.4 degrees north of west. So this is how I like to add vectors. If I have a third vector, I can just make another row here. I will do another video where I show a couple more examples, but this is the process of adding vectors. Not particularly rough, I hope. Sometimes what I need is to subtract vectors. Let's say I started with these same two vectors and I needed a vector d that was a minus b. I'm going to set up my same table. A, b, now d. And I like in my table to actually write out what I'm doing for that last one, just as a reminder. Okay, so grabbing these same vectors, I've got 3 miles, negative 6 miles, 0, and positive 8 miles. If I'm doing a minus b, then I need a negative b. Negative, a negative here makes that thing positive, and a negative here. 3 minus negative 6, so 3 plus 6, that's 9 miles. 0 minus 8, that's negative 8 miles. I'm already in component form. If I wanted this in magnitude form, what I'm reconstructing, I've got a dx, that's 9 miles. Got a dy, that's 8 miles. I'm leaving it as positive because I'm already pointing downward, and I'm going to construct my final vector exactly the same way as I did before. That's the process of adding and subtracting vectors.